Okay, so the first thing I'd like you to do before you begin today's notes, I would like you to go into Canvas to today's date, watch a video on how to use either the TI-84 in the resources or how to use Desmos, whichever calculator you have access to. You should watch the demonstration of how to use that calculator to enter data and model linear regressions. Okay, so please pause this video and go watch those videos, or one of those two videos. And then what you could do to really help today's notes go faster, once you watch that video, you could come down here and enter that data into your calculator and write your linear regression. Okay, write your linear regression using the calculator, using that demonstration, so that today's notes will go faster. So I'm assuming that you have watched that video. So what we're going to do today is just zip through these notes. So a linear regression is a linear equation calculated by a graphing calculator that represents the line of best fit. And listen, last week we were been working on writing equations of lines, right? And then on Friday we were using Google spreadsheets to take some data and to fit it on a scatter plot and then write its trend line. So we're going to use a calculator today. All right, so that's what a linear regression is. It's just a linear equation that's calculated by a graphing calculator instead of by you. All right, so let's remember that that's what a linear regression is. It's just a linear equation, and it can be written in two forms: y equals mx plus b, or if it's asked for as a function, f of x equals mx plus b. Okay, correlation coefficients real quick. They're indicated by the number or the variable r. And the correlation coefficient, we also talked about that last Friday, is just how strongly are those gap points that are on that set of data, how strongly are they correlated to a line. Okay, so correlation coefficients are between -1 and 1, with -1 being the strongest perfect possible negative correlation, and then a +1 being a perfect positive correlation. So if your correlation coefficient is 1, that means that all of your points fit perfectly on your line of best fit, and the points as x goes, as you move right, the graph moves up. So it has a positive slope, and it's a positive correlation. As one goes up, the input goes out, the output goes up. Okay, you have a strong positive correlation if your correlation coefficient is around 0.9, excuse me, 0.9. So that means that your points are pretty close to a line, okay, but they're not exactly on the straight line. However, they're still linear in the way they're trending. As you move right, the points are pretty much moving up. Okay, so that would be a strong positive correlation, which means we could still use a linear model to represent the data. If your correlation coefficient is 0.5, right, that's a weak positive correlation if, as you can see these points, the further right I go, the further up these points go. But they're pretty scattered on each side of the line, and so as you can see, the points are rising as you're running to the right, but it's a pretty weak correlation. And so a linear, if you were writing a linear function to represent that data and then predict something about more data that would come in the future, probably wouldn't be a very good prediction. If your points are scattered all about and you cannot see any kind of linear relationship between them, your correlation coefficient is 0 and there's no correlation. Going the other way, there's your information going the other way. A negative correlation just means that as you move right, your graph is moving down, and that's what your points are tending to do. But if they're pretty scattered on each side of the line, that would be considered a weak negative correlation, and your linear model might be a little bit weak in estimating data. Okay, if it's really strong, same idea here. Those points, a negative 0.9 is a really strong negative correlation. So as you go right, your points are dropping, and they're tending to do that, and they're tending to cluster pretty close to a line. And then here is your R equals -1. That's a perfect negative correlation. As you move right, the graph moves down in a perfect line. So that'll be useful when you're trying to decide whether your linear model is a good predictor of an outcome. Okay, so remember that. All right, so let's look at this data here. It says the cost of a 30-second Super Bowl commercial has increased 1.6 million. So it's gone up 1.6 million from 2010 to 2015. Model the data in the table with a linear function. Okay, so we're going to do this. So we're going to do this by hand, okay? And then estimate the cost of a 30-second commercial in 2018. So we're modeling it with a linear function. So f of x equals mx plus b, linear function. All right, so since we are modeling it with a linear function, remember what you need to write the equation of a line. You need a point, you need the slope. And what would be really nice is if you had the y-intercept and the slope, because then you really could write the equation of that line. So let's look at this data. First of all, look at the scatter plot. If I were to put a line of best fit on there, I would probably do something like that, where I have 2 points that are kind of above the line, 2 points that are below the line, and 2 points that are on the line. That's a pretty good line of best fit. All of my points are like the smallest amount distance possible from the line of best fit that I could do, okay? So let's look at our y-intercept right there. That looks like 2.9. Looks like. Well, let's take a look at this data over here. So here's our year 2010, and that's going to be x equals 0, because that's our starting value according to this information. Here's year 2015. That's going to be our x input is going to be 5. So these are our independent variables here. X is our independent variable, okay? And so that's our x. So our x is our years, and our y is the cost of a Super Bowl commercial. Okay, so it says that the cost of a Super Bowl, 30-second Super Bowl commercial in the millions for year 0 is 2.9. So that's the point 0, 2.9. First of all, I really like that point because my x is 0. This point right here is my y-intercept. So that's my b. I already know what that is, 2.9. So when we're modeling data, well, let's just go ahead and get the rest of these points. We got 1, 3.1, 2, 3.5, sorry, 3, 3.8, 4, 4, and 5, 4.5. So we have all these points. Now remember, when you're writing the equation of a line, you need a point. And if that point can be the y-intercept, all the better. And you need the slope, okay? Well, if we go back and read this problem, it says that the price increased 1.6 million from 2010 to 2015. So that gives us a rise because it went up. So that's a rise of 1.6 million over a run of 5. That's our rise over our run. So to find our slope, I would use these 2 points. You could use any 2 points that you want, though. It doesn't matter as long as you pick 2 points on the line. So we're going to do our change in y over our change in x, and I'm just going to model that data, or model what I did over here by just looking at the data and analyzing it and using the formula. So we're going to do 4.5 million minus 2.9 million over year 5 minus year 0. So that would be a change of 1.6 million over 5 years. And then I would, when we're doing linear regressions, usually our slope is just a decimal, not fraction form. So what we're going to do is just divide 1.6 by 5, and that gives us a 0.32. And that just means for every year we're going up $320,000 or $0.32 million. So there's our slope right here. And typically in a linear regression model, we would write it as a decimal. So our function, y equals mx plus b, but it does say to write it in a linear function. So we have to write it as f of x equals mx plus b. Well, we have our b and we have our m, so we can plug that in. So our function, our linear model would be 0.32x plus 2.9. Right, so there's our model. We modeled the data with a linear function. Now we're supposed to estimate the cost of a 30-second commercial in 2018. Using our model, we should be able to do that because our model does look like those points are pretty clustered around a straight line. So in 2018, well, that would be years, let's see, 2016, 2017, 2018, 6, 7, 8. That's year 8. So 8 would be our input, and let's figure out how much should it cost. So we're going to plug in 8. So the f of 8, 0.32 times 8 plus 2.9. And our f of 8 is 5.46. Excuse me. And that's 5.46 million. Because our input is years and our output is the cost in millions. Now, if we were to answer the question, estimate the cost of a 30-second commercial in 2018, you'll notice that in the problem, it didn't say what degree of accuracy is required. Here we have a degree of accuracy to the hundredths place. That's a pretty good accuracy. But when we look at the problem over here, the problem was given to us to this degree of accuracy, the tenths place. So logically, since we weren't asked to round to the nearest hundredth, we would go ahead and say about $5.5 million. So that would be the cost of a 30-second commercial in 2018. Okay, so next, we are going to compare doing this by hand to doing it with a calculator, and let's see how close we get to how close we got here with our regression equation, our linear equation, to the actual regression equation that the calculator is going to find. It says fit a regression line to the data on the cost of a 30-second Super Bowl commercial given the data on the left. Well, that's this data right here, which is the same as this data right here. It's just written in list 1 and list 2. Okay. It says use the function to predict a 30-second commercial, the cost of a 30-second commercial in 2018. Find the correlation coefficient. So we're going to have to look for that. And then answer the question, is the regression line a good predictor? All right. So we're going to start by going into your graphing calculator and typing that in. Hopefully you paid attention and you did that beforehand. I'm going to go ahead and go into Desmos where I've already done this. Okay, and I have already, I'll go ahead and take the regression equation in. So I've entered, I just went here and I added a table and then I entered my information from that table there, and there's my information. Now I'm going to add an expression. And I'm actually going to drag that up to the top. And I'm going to type in y1. So you just type in y1. You don't have to do sub or anything, just y and 1 is approximately m. There's your slope. x1, x sub 1 plus b. And then you can see that Desmos is writing the equation, and it's up in the top. I'm moving it around here a little bit so you can see it up there in the top left corner. So you can see in the statistics that it's giving you your R squared, your correlation coefficient squared, and your correlation coefficient, which is 0.9929. That is a super strong positive correlation. So you can see on the graph here that that's really a strong linear model right there. So a linear model is a great idea for modeling this data and making predictions. Okay, then also it says in the parameters up there in equation 1 that your slope is 0.314286, and your B, or your y-intercept, is 2.84762. So there we have our equation. So I'm going to go ahead and just write it down. Y equals, and then you can write it down on your note page. So this would be your answer to question 8, 0.314. No, that's really bad. Let me go 0.314 x. Don't forget the x when you're doing your homework today, plus 2.84762. I'm going to see if I can't copy that. We'll see what happens. I'm going to copy that back to my note page. And let's see if I can do it. Probably not. So I'm just going to go ahead and write it. Y equals 0.3142866 x plus 2.8. Oh, hang on a second. I wrote it down and I left my paper on a different paper. Okay, 2.84762. So you can see the degree of, or the level of accuracy that your calculator is giving you. That's out 6 decimal places, so that's a pretty accurate value. All right, and so there is your linear regression, or your regression line. Now we're going to, so let's see, let's predict, let's compare. So here our slope is 0.314, and in our original equation, when we did it by hand, we got 0.32. That's pretty close. And in our original, when we did it by hand, our y-intercept was 2.9. This is 2.8485 actually. So those are pretty close. Calculator's a little more accurate. And when you're talking millions of dollars, you want to be as accurate as possible. So you would definitely use a linear regression model to model this data. Okay, B says find the predict the cost of a 30-second commercial in 2018. So I'm going to figure out, that's 2018 was year 8. You recall we did that. So we're just going to do it in function notation, the f of 8, 0.314286 times 8 plus 2.84762. But we are going to go ahead and round to the nearest tenth, because that's the data that that's the level of accuracy, or the degree of accuracy we were given in the problem. And so that gives us 5.36. So we're just going to go with about 5.4 million. And so according to the calculator, an approximate value of a commercial would be estimated at 5.4 million in 2018. Okay, so if do I want to pay 5.5 million, or do I want to pay 5.4? I'd much rather pay 5.4. All right, so there's that. What's the correlation coefficient? We'll go back and get it. Well, I remember what it was. It was 0.9929. Okay, so that was our R value, or correlation coefficient, which is nearly perfect, positive correlation. It's almost 1. It's nearly perfect. Okay, so is a regression line a good predictor for the cost of the commercial? Why or why not? Because our correlation coefficient is nearly perfect, then a line is the best way to model this data. So how would we answer this question? And this is important because question number 10 on your homework today requires you in 30-word minimum to answer a question like this. So I am going to take my answer that I wrote and bring this up here so you can see it, and then you can just write it down or refer to it. So the question is it a good predictor? I said yes, a regression line is a great predictor, period. Or I could say because the correlation coefficient is nearly perfect. It's semicolon 0.9929, which is almost 1. It's like 99 cents versus $1. It's almost 1. Okay, so the relationship between the year and the cost of the commercial have a strong linear relationship, and that would be how I would answer that. I could also mention in my explanation, I could also mention my scatter plot and talk about how tightly those points were clustered around the line as well. So that is how you work with a calculator to do a linear regression. Now again, I did that demonstration with Desmos because that's what my iPad has options for, but I would suggest that you use a graphing calculator, TI-84, if you have it. Okay, so there you go. I'll see you guys tomorrow. Bye.